Maniacal laughter kind of loses its effect when there's birds chirping in the background. Hello. um, this is my mad scientist outfit because today we're starting our unit on electricity. No, there's nothing. There's nothing in my hair. My hair just kind of does this if you just push it up, and it stays that way. So yeah, let me know if you want to see more of this because it's not hard to do. It's so long right now too. I need a haircut. So electricity now. That's what we're on, right? Um, Before we really get into the big electricity stuff, which you usually think of like, those birds are loud, like circuits and batteries and all of that, we have to actually talk about electric charge first, right? Things have charge, positive charge, negative charge, and this is sort of the launching point for electricity. So, really, charge starts with two basic charged particles, right? You've heard of these things before: positive charged protons and negative charged electrons, right? Those are your basic charged particles. So, basically, atoms have protons and they have electrons, right? And if something is charged, well, at base, right? You've learned through chemistry that an atom naturally, generally speaking, wants to be happy with an equal number of protons and electrons, right? So it's balanced. There's a same number of positive charges as there are negative charges, and so they cancel each other out, right? And then you have an uncharged particle. But you can lose some of those charged particles, right? If you pluck out a single proton, for example, now you have one more electron than you have protons, right? So it would be negatively charged now. Although generally it's easier to pop out a electron, right? Because protons are pretty safe in the nucleus. But yeah, so say you pop out one electron, now you have one more proton than electron, right? So you have a positively charged particle there. Or if you add one extra electron, now you have a negatively charged atom right there, right? So that's how things. That's what it means to be charged. And now I've kind of alluded to our next point here. How do things become charged? First, I want to hit on an example of what you've experienced charge in your everyday life, right? So what I think that you're most likely to be familiar with, things becoming charged in life, is static electricity, right? When you go and try and touch something that's metal, sometimes you get a little zap, right? So what's going on with that little zap? Where is this electricity coming from? Is there a zap that's happening? And we're going to use two of our lovely simulations from FET, Colorado. And so the first one I want to turn your attention to is this beautiful simulation here. It's lovely, I know, right? This is John Travolta, if you don't recognize him. And so this simulation is called John Travoltage. So check this out. Voltage is a topic we'll talk about in a second, in the next lesson, I think. So our friend here, John Travoltage, is standing on a rug. And so if I take his foot and I scrape it back and forth on a rug, what do you see happening? So he's these extra blue charged, negatively charged particles, right? There's a little negative sign on those, are building up inside of him. He's getting it from scraping his foot on the carpet, right? So then I take his little finger and go near the metal knob on the door, right? So this might be a way that you get shocked. So I do that, zap, right? You see all of those little electrons go from his finger to the doorknob, and that's sort of the little zap that you're seeing. Now, as far as like what's causing them to flow and go from him into the knob is something for later lessons, but this is a good example of how he's building up, right? I scrape his foot, he's building up electrons, and now he is negatively charged effectively, and then when his finger goes down, those extra negative charges go out of him and into the doorknob. So that's a way that you've experienced charge in everyday life, and a building up charge and zapping things, right? So that's a good visual representation of just you becoming negatively charged, but they actually have another good simulation that further shows a little bit more of what's going on with the charges, and that's this balloon simulation. So here we have a balloon on one side and a sweater on the other, and this I bet you've done this without realizing it also. So watch what happens when I take this balloon and I'm going to rub it on the sweater, which you might have done with like a shirt, right? So as I'm doing that, you see that the balloon is picking up those negative charges from the sweater, right? This has to do with like just materials and what types of atoms want to hold on to electrons more than others, which we won't really get into. That's more of a chemistry thing. But you see that the balloon has taken all of the charges off of the sweater, right? So now our balloon has lots of electrons. It's very negatively charged, and in turn, the sweater is positively charged, right? Because in order for the balloon to get more electrons, it had to strip off the electrons from the sweater. So electrons and protons don't just come from nowhere, right? In order to get some electrons, you have to take them from somewhere, right? So in order for the balloon to become negatively charged, the sweater has to become positively charged, right? Because those charges had to come from somewhere. This idea is the idea of conservation of charge. We've talked about lots of conservation things. Conservation of charge isn't something we focus on as much, but this is sort of the idea. It makes sense, right? That charges have to come from somewhere. So if something gains some, something else had to lose some. But yeah, so now we've got our negatively charged balloon here. There's a little wall on that right side, right? So you've probably, this is similar to magnets actually. So watch what happens when I take our negatively charged balloon and I move it over towards the wall. You see what it's doing to the electrons in the wall? It's pushing them back, right? The negatively charged balloon is pushing away the negatively charged atoms in the wall. Like it said, just like magnets, right? It makes sense that you've seen something like this where negative or where similar charges repel each other, similar poles on a magnet repel each other, and then whether that's negative, negative, or positive, positive. And the other side of that, right, is opposites attract. We've heard that before. So watch what happens if I release the balloon. It moves over to the sweater. Because now, like we've said, the balloon is negatively charged and the sweater is positively charged. So they have opposite charges, meaning they'll move towards each other, right? So if I release the balloon, they move together. That's pretty intuitive, right? Like I said, it acts like magnets. So yeah, that's kind of how attraction works with electricity. So I think that's pretty intuitive. It makes sense. It works like magnets. The last thing that I wanted to talk about is connected to how you're becoming charged by picking up actual individual electrons. So when something is picking up individual electrons, it's increasing its charge by one electron, right? If you get one extra electron, you have one more electron of charge. And so individual electrons actually have a consistent charge. So there's a big long number that goes into charge. Charge is measured in what's called a coulomb, named after Coulomb science dude, whatever, you know how those work. So it's called a coulomb. It's represented by a big capital letter C. And so an individual electron has a charge of 1.6 times 10 to the negative 19 coulombs. Very small. It's a little bitty electron, right? So very, very, very small, but that's the charge of one single electron. 1.6 times 10 to the negative 19th coulombs. Now, if you are at a base happy state, you have the same number of protons as you do electrons, and then you pick up one extra electron now, you are negatively charged, right? You now have one more electron than you do protons. And so you now have a net charge of 1.6 times 10 to the negative 19 coulombs, right? You have one electron of charge because you have one more electron than you do protons. And so this is kind of getting at an idea of if something is charged, it has to be a multiple of that electron charge, meaning that if you have some sort of charge, you have to have a certain number of extra or missing electrons, right? So if you're charged with 100 electrons, right, then your charge would be 1.6 times 10 to the negative 17th coulombs, because you have 100 electrons worth of charge. Basically, anything that has a charge, you should be able to divide that by the charge of one electron, and you should get a whole number every single time, because you can't have a portion of a electron worth of charge, right? You can only have a whole, you can't have half an electron and have half the electron charge. You basically have to have a whole number of additional or missing electrons to have that amount of charge, because protons have an equal and opposite charge. It's just like a positive versus a negative 1.6 times 10 to the negative 19th. So you might run into problems like this. I believe there's one in the exit ticket where you just, if you have a charge, it has to be a multiple of the electrons. You have to be able to take that charge, divide by 1.6 times negative 10 to the negative 19th, and if you don't get a whole number, then apparently you don't have a whole number of electrons, which doesn't work. That doesn't make sense. You can have half an electron. So yeah, that's a good way to check tests like these sorts of questions where it's like, which one of these is actually a charge that works, or which one of these isn't a charge that works, and it's whichever one that you don't get a whole number of electrons for. So we'll look at an example really quick. I'll get the whiteboard. So basically, say that you have, I literally will just use the example that I verbally said, but I'll write it down so you can see it. Say I have a charge of 1.6 times 10 to the negative 17th coulombs. That's my charge. And the question's asking you something like, how many electrons how many extra electrons does Mr. Foster have in his body or whatever? It might be asking you which one of these is a real charge or whatever, but it could be asking you this. And so the way that we solve this is it works a lot like a unit conversion, the way that you would have set it up in chemistry, right? So we know that one electron has a charge of 1.6 times 10 to the negative 19th coulombs, right? So to solve this for our number of electrons, right, because coulombs would cancel out, you're basically just taking that charge and dividing by the charge of one electron to see how many electrons I have extra. And in this example, right, you get 100 electrons. I have 100 electrons. And if I would have come out with a decimal here, right, where I wouldn't have had a whole number of electrons, it wouldn't work out. That doesn't make sense. Can't have half an extra electron. Can't do that. It has to be a whole number. So yeah, that's what you do with these problems. Is basically just take that charge, divide by the charge of one electron. If you don't get a whole number, it's an impossible charge. Pretty straightforward, I think. I think that makes sense. Yeah, that's kind of what you do with charge. We don't look a lot at charge. There's attraction, repulsion. You know that protons have positive charges, neutrons have negative charges, and that the charge of an electron is 1.6 times 10 to the negative 19th coulombs. Although that's given to you, that's one of those numbers that you don't have to worry about. Yeah, that's kind of what charge is. It's just needed a little bit of an intro for like what is electric charge, so that we can launch from there. But this lesson's pretty straightforward. Good luck with the exit ticket. I hope you enjoyed my hair, and I hope you enjoyed the John Travolta simulation. But with that, that's all we got. Easy video today. Bye.
Kazam!